the emergence of the principle of soil mechanics, geotechnical engineering. So the most famous example of a soil mechanics problem is the Leaning Tower of Pisa. Nasabi na rin to ni Ms. Castrence kanina sa kaninang slide. Then it took 344 years to build. That begins to in August 1173 and then it began to lean in 1178 once construction on the second floor had begun. So the lean was due to one side sinking into the soft ground. So kung isipin nyo, why didn't the designers expect the tilt? Kasi when designing a tower, tilt was probably not part of the original plans. However, the architects overlooked the fact that the tower was to be built in a parang swampland. So because of that, it is the emergence of the principle of soil mechanics. Because engineers starts to develop a scientific approach to setting a foundation of buildings with respect to soil design and structure. And later on, a French engineer named Henri Gautier recognized that natural slopes of different soils is also the soil's angle of repose. And then more principles of soil mechanics began to emerge.
Okay. So next is the importance of geotechnical engineering. It will be reported by Kuya James Darelle Dinio.
The importance of geotechnical engineering. First of all, the most important or the thing that we need to know is to understand the soil or what will happen, what is the happening under the structure that we had, in order for us to first to have a safety, to lessen the risk and hazards to human and properties that may cause if hindi natin nalaman kung ano yung mga dapat nating paghandaan sa itatayo nating structure. If you fail to understand the components of the soil rather, first makikita natin magkakaroon tayo ng settlement. On the first picture, it is see that the house bumaba yung bahay kasi hindi naalaman kung ano yung components. Ibig sabihin hindi kinaya ng bigat nung bahay yung lupa, hindi kinaya ng lupa. Then second is yung paglubog ay hindi naman naging totally pababa, which is naging dahil hindi pantay-pantay or not equal yung uri ng mga particles sa ilalim ng lupa. Ang nangyari ay ilang parts lang ng baha ng structure natin ay lumubog. That may cause the deform and the crack. And lastly, on the right picture, it may also cause the foundation failure, which is sabay-sabay or all parts has been affected by the failure to understand the components of the soil. Whereas kapag hindi natin binigyang pansin ang geotechnical engineering, hindi natin siya kinonsider sa pagtayo ng ating structure, more or less mag-fail yung ginagawa nating structure in the near future. Kagaya na nangyari sa Leaning Tower of Pisa. Next.
So next in our discussion is what does a geotechnical engineering do? It will be reported by Ate Cherry May Castrence.
So next is what does a geotechnical engineering do? So ano nga ba yung ginagawa ng isang geotechnical engineer? So geotechnical engineers guard and maintain the Earth's physical environment during the development of major public and private projects. So basically yung geotechnical engineer focuses on research and study of the soil para ma-evaluate kung suitable nga ba siya sa pagtatayo ng isang structure. So, ang geotechnical engineering is divided into subtypes. Meron siyang ang una is yung geotechnical or geological engineer in general. So, ito yung nagpa-provide ng analysis and mapping of technical results na nakuha sa seismic service. And siya rin yung nag-investigate ng subsurface conditions and materials to determine their properties and risk. Second is the geotechnical or geological engineer in oil sand projects. So sila naman yung nagde-design ng open pit walls, mine waste dams, and dam structure. So basically sila yung nakafocus sa mga dump waste, sila yung nakafocus sa mga dams. Next one is the hydrogeological engineer. From its word hydro, meaning focus ito sa water aspects. So it provides design and analysis of ponds containing discarded oil sand materials, water extraction from oil, soil and sand, and steam injection into wells. The fourth one is the reservoir geomechanics engineer involved in oil and gas operations. So sila naman yung concerned sa tibay ng lupa. Sila rin yung nagdi-drill ng holes para sa stability. So sila yung involved dun sa pagpapatibay ng lupa na paggagawa ng isang structure. The last one is the geomechanics engineers in marine operations. Sila naman yung nag-a-analyze ng relationship between physical structures and marine geology, anchoring systems, sediment erosion, slope stability, and foundations for offshore and coastal structures. Next po.
Next is, what is the workplace of geotechnical engineering like? So as you can see in this slide, let's first define ano yung workplace. So it is a location where someone works or a place of employment. So geotechnical engineers, minsan nasa operation sites, but they are not always there because geotechnical engineers are usually work in a comfortable office setting. So geotechnical engineers, as we go on in the next slide, can be employed by the following types of organizations. So, una sa listahan dyan sa mga ay ang colleges and universities. So, alam naman natin na hindi lang naman sa mga operation sites yung mga engineers niya. Kahit anong engineer yan, pwede rin silang pumunta sa mga academe para magturo. So, next is, they can also be employed also in public and private research organizations, construction contractors, engineering consulting firms, and also in municipal, regional, and federal governments. So they can also work with different companies, katulad ng electrical utilities, sa mining, sa oil and gas exploration, production and transportation, petroleum services, and real estate development companies.
finished, everything was noticeably leaning to one side. Thanks. In 12th century Italy, the tower was under construction in the town of Pisa. The design was for a beautiful freestanding bell tower. Construction of the third level began. Something went wrong. The whole tower began to tilt, and by the time it was finished, noticeably leaning to one side. Thankfully, the mistake was seen as charming by visitors, and eventually it turned into a global icon and a tourist attraction. But for the Civic Tower in Pavia, which was built around the same time, structural problems led to a fatal collapse in 1989. The next year, a team of Italian engineers was formed to prevent the same fate in Pisa, while maintaining the tower's iconic tilt. For both buildings, the problem wasn't just above the surface. It had to do with the support of the foundation underneath. And since modern structures can be many times larger, the stakes are much higher. You definitely don't want a leaning skyscraper on your hands. So to keep things standing tall above ground, you need to look at what's going on below it. Do we need for the places we want to live? Roads, bridges, tunnels, and ports all require planning to build and maintenance to keep working safely and efficiently. And infrastructure supports vital networks like water and power supplies. In fact, the US National Academy of Engineering has made repairing and improving infrastructure one of its grand challenges for the 21st century. And as we learned in Pavia, a structure that's going to last needs to be on a solid foundation. And that's where geotechnical engineering comes in. At least for now, the infrastructure we build is connected to the ground. Even the sturdiest, most well-designed building won't last if the land supporting it isn't up to the task. So geotechnical engineers spend a lot of their time investigating the rock and soil that structures are going to be built on. As well as building on top of the ground, engineers often dig into it, like for a harbour or a dam, or tunnel through it, as in the case of underground train tracks. In each of these scenarios, you have to consider how the ground's characteristics might affect the structure's stability, a consideration the designers of the Tower of Pisa overlooked. We've seen before how forces like crosswind and the weight of the materials can affect a building. Many of the same lessons apply here. The foundation of a structure is the part that actually connects to the ground and transmits forces to it. So that might be columns or walls that extend into the ground, for example. And they're as much a part of the structure as the bits we can see. To stop a building from falling over, sinking, or snapping, it needs to be supported through its foundation by a reaction force. In other words, the soil needs to resist the force transmitted through the foundation. Soil might seem pretty straightforward. After all, it's just dirt, right? But in reality, soil is one of the most complex environments engineers work with, and it comes with a lot of variety. Just like other materials and fluids, soils and even rocks have mechanical properties that make them suitable or unsuitable for building on top of. If enough force is applied, the ground itself can shift and change shape in intense ways. The capability of the ground to withstand those forces is its bearing capacity. How much force can be transmitted over a given area without causing the ground to drastically change shape. Just like a solid material, soil can actually undergo failure in the mechanical sense. At that point, it no longer fully supports the structure, which is what happened to the Leaning Tower of Pisa. The foundations of the tower weren't deep enough to support it after it reached a certain height. That meant the stress applied on the tower's mass bigger than the soil's bearing capacity, which ultimately shifted the ground and tilted its foundation. Bearing capacity is tricky to calculate, but essentially it depends on both the depth and the design of the foundation and the qualities of the soil that you're building into. Since you usually can't control the soil, you need to understand it and build a foundation that accounts for any potential problems. The main property you'll be interested in is shear strength. As the foundation applies the load to the ground, the soil redistributes the force, creating tension throughout the region around it. Just as we saw for materials, everything has a certain internal resistance to shear stress, the kinds of forces that act in opposite directions. There are other kinds of stresses to consider, but shear stress is the most important because it's the one most likely to lead to failure. Layers of soil that push past each other can quickly stop supporting the structure's foundation. The shear strength is the measure of the shear stress the soil can tolerate before it reaches failure. The higher the strength, the more stress the soil can resist before it finally gives way. It's one of the biggest factors that determines the bearing capacity. You generally want the soil to be as strong as possible to ensure as much stability as you can. The trade-off is that stronger soil can sometimes be a little trickier to excavate in the first place, and some structures, such as bridges, have to be built in particular locations. So you often have to work with whatever soil happens to be there. The key to understanding the strength of a particular piece of ground is that soil isn't one homogeneous thing. Instead, it's best to consider soil as a collection of tiny grains of rock and leftover organic matter from living things. The exact materials differ between soils, but in geotechnical engineering, the focus is on size and shape of those grains. That's where the soil gets its strength or weakness from. It helps to think of the concept of viscosity, which we encountered in fluid mechanics. When the soil undergoes shear stress, the friction between the layers of soil helps resist the stress and give it solidity. One of the causes of that friction is that the grains interlock with one another and resist any change to their arrangement. If things do move, there's the added friction of the particles rubbing together. Both of these contribute to the shear strength. Separate from friction is what's called cohesion, or the tendency for smaller particles to stick together, like in modeling clay. In fact, it's often tiny particles of clay or silt that are responsible for cohesion in soil. So the more clay it contains, the stronger it will be. The size and shape of the grains and the cohesion between them are just some of the properties geotechnical engineers use to estimate shear strength. The full picture would take into account all the complexities of the soil, including its mineral composition, moisture levels, and the size of the grains themselves. Not to mention the fact that strength isn't constant throughout the ground. It can be radically different for buildings on opposite sides of the street, or even at different depths under the same structure. So you'll want to be sure to do a detailed analysis. That will guide you in designing a foundation that provides the bearing capacity needed for what you're trying to build. In 1990, a year after the Pavia Tower collapsed, the Italian government set up a team of engineers to tackle the problem of Pisa's bearing capacity. In the weak soil underneath the Pisa Tower, 3-meter deep foundations weren't enough and the tilt was slowly getting worse. After trying different approaches, engineers finally weighed down the side of the tower opposite the tilt with lead and removed some of the soil from that side. In doing so, they managed to sink the foundation a little further into the ground, increasing the contact area between it and the soil and improving the bearing capacity. The shifted weight of the tower even compressed the soil at its foundation, actually improving the soil's strength. Now it's thought that the tower should be safe for at least 200 years, all while retaining its iconic lean. While that's great news for Pisa, other parts of Italy are prone to a different ground-based problem. Because of fault lines in the Earth's tectonic plates, regions in Italy are susceptible to earthquakes, like other areas across the world. In 2016, a powerful quake caused devastating damage to the buildings in central Italy. Protecting against the effects of earthquakes is exactly the task that seismic engineering is there to tackle. That's why these people are often known as earthquake engineers. While they share many techniques with geotechnical engineers, seismic engineers have to worry about what happens when the ground itself starts moving. A violent movement can subject the foundation of a structure to a load larger than its bearing capacity can handle. Worse still, the soil might undergo what's called liquefaction, in which loose, sandy soils lose virtually all their strength and behave like a liquid, which spells disaster for anything built on top. In addition to modeling the soil like geotechnical engineers, seismic engineers have to break out the full toolkit of statics and dynamics to understand the whole structure. In fact, because the effects of an earthquake are tricky to simulate, seismic engineers often use what's called finite element analysis. They use computers to model every piece of a structure and predict the exact stresses and strains each piece might feel. Just to be sure, scale replicas of entire buildings are often built and tested on oscillating platforms to demonstrate the real physical effects of an earthquake. While destroying a model bridge might sound fun, the goal is to test designs and see where faults arise so they can be made safer. In combination, geotechnical and seismic engineers make sure that structures remain standing tall from top to bottom when they encounter stress at their foundations. In environments dense with infrastructure like cities, it's a critical job for the safety of everyone nearby. And this means we can continue to enjoy the Tower of Pisa for centuries to come. In this episode, we looked at geotechnical and seismic engineering. We learned.
So that's all, guys. This is the geotechnical engineering orientation report, and
how structures connect to the ground.
thank you for listening, guys.